For question number 2, the correct options are A, C, and D. And to show how we got them, let me show some steps of solution. In step number 1, we should draw a quick figure to understand what they're telling. This is the floor of the tank on which stands a liquid layer of small thickness, and on top of which the thin square plate floating. So this is the floating plate, this is the floor of the tank, this is the viscous liquid in between of depth h, and an external force applied to this floating plate is making this plate move with a constant velocity of u0 to the right. This blue arrow represents velocity vector u0, green arrow represents external force applied onto the plate, and as the force is applied by the agent outside, this viscous liquid now exerts a force to resist the motion of the plate, and that force I am showing here on the bottom face acting towards left and tangentially. So generally we call this force as Ft, T standing for tangential, and is further given that for this liquid viscosity coefficient is eta. So the question is, what is the magnitude of this viscous force? We have this Newton's formula, let me write it. Newton's formula for laminar viscous flow. Ft is equal to eta into A into dV dy in the exact form. I'll explain it. Here Ft is of course viscous force acting tangentially on this plate opposite to its motion. Eta is viscosity coefficient of the liquid. A is the area of the bottom face of this plate. If I could show you a 3D figure somehow here, let me show it. It's a 3D view of this plate, and I'm talking about this bottom face. Follow my cursor. This line is the outline, and then these two lines shown in dashes, they are hidden. So that bottom face has got an area of AC, right? So that area is also coming in this formula. And what is dV dy? That is called speed gradient. The liquid layer in contact with the floor is at rest because the floor is at rest. On the other hand, liquid layer in contact with this moving plate has a velocity of u0 only. So the speed of these liquid layers continually changing from 0 at the bottom to u0 at the top just in contact with the plate. And in case this speed does not vary linearly with distance from the floor, we use this dV dy, that is the rate of change in speed of liquid layers with distance measured from the floor of the tank. The general case. But in case we take h to be very small, as in the question they are telling, h is small enough, in that case, this formula becomes easier. Ft is equal to eta into A into, well, dV standing for the change in velocity. Velocity is u0 here, it is 0 here. So velocity change is u0 divided by this length, that is simply h. So we shall use this last equation 1 to verify various options given in this question. So in step number 2, let us see what we can conclude from this equation and compare that with the different statements given in the problem. We can write down other conditions remaining the same. This resistive viscous force Ft is proportional to 1 upon h. And the statement A, resistive force of liquid on the plate is inversely proportional to h. So that is correct option. Option A is correct. We can write next other conditions remaining same. This viscous force is proportional to the area of the bottom face of the plate in contact with the liquid layer. But the statement B telling resistive force of liquid on the plate is independent of the area of the plate, but that's not correct. We are seeing here the force varies directly as the area of contact. Therefore, our conclusion is the option B is wrong. Next, you can see from here that if I bring A to the left, you can write down Ft by A, that is equal to eta into U0 by H. This Ft by A, that is the tangential force per unit area, that is nothing but tangential stress or shear stress, and is showing that this shear stress Ft upon A is proportional to U0. And option C, the shear stress on the floor of the tank increases with U0. That's again correct. You can see here shear stress varying directly as U0, the speed of the plate. So option C, that is correct. We can write further that this shear stress Ft by A is proportional to eta, other conditions remaining the same, and the option D was shear stress varying linearly as viscosity coefficient eta. That's once again a correct statement. Take D to also to be correct. So seeing here, options A, C and D are correct and B is wrong, thanks to this Newton's formula for laminar viscous flow.